Hello everyone and welcome to this presentation. My name is Ping-Hsuan and I'm from Taipei Tech. Today I'm excited to share our research on Hit the Round, substitutional moving robot for immersive and exertion interaction with encounter type haptic. In this talk, I will walk you through our system design, key finding, and the potential of this technology in the future XR experience. So let's just get started. Previous research have revealed the potential of combining VR technology with sport or exercise. However, those exertion interactions do not have to consider the fear force from humans. Specifically for the combat sport, the interaction would involve user full body strength and movement, which the substitutional robot design should allow user to walk freely and simultaneously beat the block. In the previous word, rooms should provide a room-scale dynamic haptic environment with a movable robot. While the robot can carry the furniture, they cannot absorb the fear force from humans. Co-VR created a robot that provides the vital kinetic feedback in VR. Nevertheless, the system must install in the ample space, and the movement is restricted within the structure. Our work aimed to create a durable moving robot, allowing users to engage in the full body straight interaction within the immersive exertion environment. Comparing to the previous work, we're focusing on creating high mobility and low endurance substitution robot for immersion exertion interaction. We present Hit Around, a substitutional rowing robot for immersive and exertion interaction with encounter type haptic. We developed three prototypes iteratively to explore the design consideration for developing a substitutional moving robot and demonstrate them separately in three exceptions to collect the user feedback and gain the insight into the immersive exertion interaction by exploratory observation study. The first prototype used plastic and pipe as the base structure and an airbag as a beatable prop to provide the haptic feedback. During the exhibition, we observed that while the airbag allowed the user to throw punches and experience encounter type haptic feedback, it could not provide a continuous haptic feedback. When user punched their airbag, it would immediately fall away from their glove, creating a sensation more akin to hitting a bouncy ball than a solid object. So the second prototype aimed to explore the continuous encounter type haptic to enhance the endurance of the prop. We replaced the airbag with a water airbag. During the exhibition, the robot successfully provided continuous encounter type haptic feedback when the user punched the prop. However, the base structure center of gravity was positioned too high. The volume of the water in the water airbag not only increased the robot overall weight, but also raised its central gravity as the water level increased. In the third version, we shortened the aluminum bracket, increasing the base weight. This maintained the heavy weight, but with a lower center of gravity. We add fine damper around the water airbag to absorb the stronger punches and transmit the force to the ground. We sort out our prototype information as follows. For more detail, please refer to our paper. Based on the iteration, we converged three topics for design consideration. When designing a movable robot to carry the prop weight significantly affects the robot mobility. While heavier props provide greater stability and offer more resistance for encounter type haptic feedback during the punches, they reduce the robot's maximum movement speed. However, the ideal prop weight depends on the training focus. Flyweight boxer might prefer a heavier prop for the power training. Adding more water to the water airbag is the simplest way to increase endurance in our system. However, this raises the center of gravity, increasing the likelihood of the robot losing the control or tipping over. To prevent the wheel from leaving the ground, the center of gravity must remain low. While simulating the virtual object to resemble in physical counterpart visually may seem intuitive, aligning the physical product with the virtual avatar requires thoughtful design, especially when their shape different. For aligning strategy can be employed, making the virtual and the physical object appear or feel similar in shape, aligning the majority of the avatar punch surface, aligning only the target point and displaying one target at a time allowed. If the virtual avatar is larger than the physical part, placing the virtual target point shallow within the physical part encourages the user to punch deeper. In the system overview, the user will enter the virtual world and combat the virtual avatar and receive the haptic feedback from the substitutional moving robot. Dividing into the hardware design, we designed the force absorption mechanism. Our system had three passive components to absorb the force from the user punch: the water airbag, the buffering cuff, and the wheel and passive sway wheel. The Raspberry Pi controls the movable-based structure to regulate the speed of the hub motor. User can use a tablet or a computer to connect the Raspberry Pi via Wi-Fi and then send signal to control the movement speed and direction of our devices. For the robot movement design, it includes forward, backward, rotating around the wheel, and rotating in place. To integrate the virtual and the real environment, we designed the calibration function to make the physical prop into the virtual world. We also conduct a technical evaluation to test the robot's feasibility with 4 power mode and 6 weight. The maximum motor power for a straight line test was set to the 50%, as exceeding this without a weight load could cause the device to move too quickly. On the other hand, less than 20% power was insufficient to move the robot. We conducted a straight line running test and rotating test, and found the power influence larger than the loading the weight in our robot. To demonstrate the hardware capability and how it can be integrated into the VR experience, we designed an exert game. The user will face a virtual avatar and have a punch to the target with their punches. Then we conduct a study with 24 participants to confirm the hit around, enhance the immersion, and ensure the comfort during the interaction. The results were analyzed using an ANOVA for VRSQ, IPQ, and PACE8. Our between subject variable were having boxing experience, while the within subject variable was 3 kind of interface: no robot, fixed robot, moving robot. We found out the participants respond to the VRSQ subcategory, which are ocular motor and disorientation, have no significant difference in pre and post test in their interaction. Expected, the disorientation has significant difference in interface. We consider that it was because of fatigue. For the physical enjoyment, interface has significant difference. While the participants receive haptic feedback, they feel more enjoyment during the activity, but there is no significant difference in having boxing experience. For the immersion, participants report that while receiving the haptic feedback, they feel that they were more likely to experience a realism activity. Besides, moving in the virtual environment made the participants feel more physically involved and further enhance their involvement. However, there is no significant effect on having boxing experience or not in the IPQ. Next, we conduct a field deployment with 69 participants to explore how the general public feel about our system. The results showed that after experiencing it around, participants feel that their stress was released, being more delighted, and also had a sense of tiredness. Some participants say it felt like playing a whack-a-mole game with racing. Others say I imagine punching my boss face, which really let me feel stress release. In final, there are still some limitations and challenges for us to solve. Our moving robot enables the full body interaction for combat sport, significantly enhance the fatigue, enjoyment, involvement, and special presence compared to the no robot and fixed robot condition. Although we designed a substitutional robot while implementing in different fields, it still need for the further design for better adaptation. We found that most participants feel their hand in the robot were precisely positioned in the virtual world. Participants with the boxing endurance thought the position in the virtual world should be more accurate because the shape difference between the avatar. Thus, exercise in the virtual VR should consider more on the user safer concern. In this work, we present the Hit Around, a substitutional moving robot that allows users to experience immersion, exertion, and action in VR. In the future, we will develop a more adaptable version for different physical environment and design a better virtual environment to enhance the user experience in immersion, exertion, interaction. Thank for your attention.